Okay, we're going to review rational functions and inequalities. So to find the y-intercept for a rational function. So first, see down here, you can see a rational function, right? It's the quotient of two different polynomial functions. So to find the y-intercept, you're going to plug in 0 for x. So let's talk about the rules while we complete this first problem, just to see the rules in action. So if I plug in 0, I would get 0 divided by 6, which is 0. So my y-intercept is 0, not 0, 6, 0, 0. Next, my x-intercept, technically we're plugging in 0 for y. But if I plug in 0 for y, I'm plugging in 0 right here. What's the first step? Take the denominator, x plus 6, and multiply it to the other side. 0 times anything is 0. So now I just have 5x equal to 0. So kind of the shortcut is set the numerator equal to 0. So if I'm going to set the numerator equal to 0, 5x equals 0, so x has to be 0 again. It makes sense in this problem that if the y-intercept is 0, the x-intercept will also be 0. So we can plot that on our graph. Finding the vertical asymptotes, that is when we set the denominator equal to 0. So we're looking for the undefined values in the denominator because that's when our function is going to be undefined. So x plus 6 is our denominator. So when x is negative 6, then the denominator would be 0. To write the equation, we'd write x equals negative 6. And to graph that, we would put a dotted vertical line at negative 6. Horizontal and slant asymptotes have 3 rules. So the first rule is if the numerator is a bigger power, there's a slant asymptote, and you do division. So that's not the case here. We've got 5x over x, so they're actually equal powers, linear divided by linear. Number 2, the numerator is equal to the denominator. You're going to strip the coefficients of x. So my coefficients of x are 5 and 1. 5 divided by 1 is 5. So my horizontal asymptote is at y equals 5. So I would do a dotted horizontal line at 5. My final rule for horizontal or slant asymptotes is that the denominator is bigger. And whenever the denominator is bigger, when you plug in a large number, it blows up. So you have a number divided by a huge number. And so that always will approach 0. Y equals 0 would be the denominator. To find a whole, if you cancel factors, plug the originally undefined x value into the new function. So we didn't cancel anything in number 1, so there's no whole. So I'll show you what that means when we get to another example. So let's finish graphing this. So I can see in this quadrant, the graph must be approaching this asymptote and this asymptote, and it went through 0, 0. Something must be happening up in this quadrant, so I should plug in a number like negative 7 and see what happens in my function. So if I plug in negative 7, I get negative 35 divided by negative 1, which is 35. So negative 7, comma, positive 35 is like way up here, right? So there's something going on way up here in this quadrant. So you always want to check a value to the left side of your asymptote so that you know where that other region of the graph is if there's no identifying x or y intercepts. So let's follow those rules again. To find the y-intercepts, we plug in 0 for all of the x's. So I would get 0, I would get 0 divided by 2 is 0. To find the x-intercepts, we set the numerator equal to 0. So we should factor this. If I factor this, I have x squared times x minus 4. So I actually have two x-intercepts, one at 0 and one at positive 4. 0, 0, and 4, comma 0. So I should plot 4, comma 0 as another x-intercept. Find the vertical asymptotes. So that is where the denominator equals 0. So I'm going to factor this, x plus 2 times x plus 1. I found the factors of 2 that added up to 3. I skipped the diamond method, but you're welcome to use the diamond method to get here. So my two vertical asymptotes are at -2 and -1. X equals -2, x equals -1. So -2, this is going to be a tricky graph, I can tell already, and -1. So to find the horizontal or slant asymptotes, I should also mention that no factors up here could cancel with any factors in the denominator, but you should always check that step. So now I'm going to take this function and divide by this function using the box method. So I'm just going to do that on another sheet of paper. So what you're going to do is you're going to draw your box, and you're going to put x squared, 3x, and 2 down the side, because that's one of your factors. That's your divisor. Now we want our dividend, this number, to end up inside the box. And up here, we're going to get our quotient. So I'm going to take x cubed and put it inside my box. So now what has to go up here? X, because x times x squared will give me x cubed. So now I take this x and I follow down in these two boxes. So this would be 3x squared and then 2x. So this box and this box have to add up to the dividend, -4x squared. So this has to be -7x squared. If this is -7x squared, that makes this -7. And this is your slant asymptote. If you want to finish the division, you'd have -21x minus 14. And as you can see, there's no other terms of the actual dividend. So I already have x cubed, I already have -4x squared. So I actually need this to equal 0. So if I have -21x and 2x, I need an additional 19x and an additional 14 so that I have 0 for the rest of those terms. So my remainder is actually 19x plus 14. All I care about is that the slant asymptote is y equals x minus 7. Y equals x minus 7. So what does that look like? That would go through -7 as a y-intercept, and it would go up 1 over 1, up 1 over 1, up 1 over 1. So here's my other slant asymptote. And this looks like kind of a tricky graph. So this is not one that I would have you finish graphing by hand. I'd have it with graphing calculator as a resource. So x cubed minus 4x squared. Make sure you put them in parentheses if you're looking at a calculator. X squared plus 3x plus 2. Graph it. Yeah, see, I would not have been able to kind of get that type of graph without this. So it kind of goes like up, cuts through, and then, oh, bounces, it must bounce off right there and then go back up towards, so it's approaching this asymptote and maybe approaching this asymptote. So kind of a really yucky graph, but I just wanted you to practice that division for a slant asymptote. All right, here's another situation. So maybe you want to pause the video and then go back through my notes to see if you get the same answer. Plug in 0, so I would be at 1/3 because 8 over 24 is 1/3. The x-intercept, there is none because 8 will never equal 0. The vertical asymptotes, this factors into x minus 6, x minus 4, so they are at positive 6 and positive 4. Actually, I'm just going to write x equals 4. So two separate equations. 1, 2, 3, 4. Here's x equals 4. And here is x equals 6. So kind of a strange graph again. Whenever you've got multiple regions, it kind of changes that, like the easy rational functions have just the two regions. So when you start breaking it into more regions, it's a more complicated graph. This is going to have a horizontal asymptote at y equals 0 because the denominator is bigger. So normally I would say just plug in an x value over here, but with so many different regions, this would again be a graphing calculator type question so that you could look at this step on the calculator. So let's see what it looks like. Oh, remember I do have y equals 0 that I forgot to put in there. So it looks like this part goes like this through that x-intercept. And then you've got this little blip down below. So if I plugged in, what number is this? 1, 2, 3, 4, 5 into my function, I get 8 over 25 minus 50 plus 24. So that's 49 minus 50. Wait, is that right? Yep, so I'd get negative 1 in the denominator and 8 divided by negative 1. Oops, this really should have been at negative 8. So it's kind of an upside down little parabola there. And then up here in this region, I could plug in 7. If I plugged in 7, I would get 2 and a third. So 7 comma 2 and a third. So this part of the graph's kind of looking like little volcano-ish. So again, for answering these like one-off questions, you should be able to answer these 4 questions. Putting a difficult graph together like this you'd have a graphing calculator for. This you might not. All right, number 4. So before we start, we should factor the numerator and the denominator to make sure there's no factors that could be canceled. So let's see, this would be x plus 5, x minus 2. And then the box method for this part of the problem, 2x squared negative 2. The diamond would be negative 4 up top with a negative 3. So negative 4 times 1, negative 4x, positive 1x, 2x times 1 times negative 2. So I do end up with a repeated factor. So I have 2x plus 1 and I have x minus 2 again. So I just canceled this x minus 2. So remember before I said you're going to plug the undefined value into the new function? This undefined value would have been at 2. So I'm just going to write down 2 comma something so that when I get to the whole, I'm just going to plug 2 in up here. Actually, let's just do that. So I'd have 7 divided by 5. So 7/5, 2 comma 7/5, there's a hole, and the graph is going to go through there. So now I'm going to answer all the questions about this function right here. I'm going to ignore all the other functions. This is my new function. To find the y-intercept, plug in 0, so I have to get 5, 0 comma 5. Find the x-intercepts, I'm going to plug in, or I'm going to set the numerator equal to 0, so negative 5. 1, 2, 3, 4, 5. The vertical asymptote, the denominator is undefined at negative 1/2. That is where it would be equal to 0. So x equals negative 1/2. This is going to have equal powers. So when I strip the coefficients, 1/2 is going to be my horizontal asymptote. So let's see, 7, I should have done 7/5 up here, right? 7/5 is more than 1. Oops. So this is a dotted asymptote at 1/2. So that point's not really there. Okay. And I already have the coordinate in my hole. So it looks like I can see what this side of the function is doing. It must come down here, go through the y-intercept, go through the hole, and hug this asymptote here. And this side must hug this asymptote, come down through, and then hug this asymptote. All right, and this little problem at the end here, we're looking for when you have a function on one side of the inequality. So if I'd subtract 12, I want to know where this parabola is above the x-axis. So if you have to solve this algebraically, and then I'll show you solving it graphically, you would have to factor this first. I'm just going to do this with my shortcut. If this is a prime number, you know that it has to be 2x times x to get 2x squared. Now you're just looking for some factors of negative 12 that are going to make this true. So like maybe 4 and 3. And 4 and 3 will work, I think, because if I put the 4 here, 2 times 4 is 8, minus 3 would give me 5. Or go ahead and do the box method. So once I have my factors, I know that 3 halves and negative 4 are my x-intercepts. So I'm going to plot negative 4 and 3 halves on a number line, and I'm going to test a value that lies in each of these regions. So I'm going to take negative 5 and I'm going to plug it in up here into my greater than here one. If I plug in negative 5, I'd have 2 times positive 25 minus 25 minus 12. That would still be positive, right? 50, and then I'm not subtracting 50. Do I want it to be positive? Yes, I do. So this region works. What do I get when I plug in 0? I get negative 12, which is not positive. Doesn't work. What do I get when I plug in 2? I get 2 times 4 plus 10 minus 12. This comes out, this is bigger than this, so this comes out positive. So it works. So the way you answer an inequality is with inequalities about these regions. So x is either less than negative 4 or x is greater than 3 halves. And what does that actually mean? So when I look at my y equals and I plug this in, 2x squared plus 5x minus 12. So I'm going to plug in the new one that I got when I solved it. And I'm just going to look at that parabola. I want to see where it is above the x-axis. So coming off of this x-intercept, so when it's to the left of negative 4, and to the right of this x-intercept, so when it's to the right of 1.5. So that's what this says, when x is less than negative 4 or x is greater than 1.5. So that's the solution to that inequality. And part B, this is a rational function. So on this one, the x-intercepts are critical values. So we call them critical when we use their bubble on the number line. And this is x-intercept and vertical asymptotes are critical values. So I have one x-intercept. First of all, this is just greater than 0, so that it's set up for me to look at. I would have an x-intercept at 0 and a vertical asymptote at negative 3. So a graph can change at asymptotes and at x-intercepts. So I'm going to plug in negative 4. What did I say this was? 0. So negative 1 and 1 into my original inequality here. If I plug in negative 4, I get negative 20 divided by negative 1, which is positive 20. Hey, that's a positive number. I want positive numbers, greater than 0. If this said less than 0, you'd be looking for the negative numbers. When I plug in negative 1, I get negative 5 divided by 2, which is negative. If I plug in 1, I get 5 divided by 4, which is positive. So my answer is x is less than -3 or x is greater than 0. I did not show you an example when this region won, but if this region won, this would be an AND inequality. So I'm just going to write it down below and then cross it out. You would write it as -3 is less than x, which is less than 0. This says just the center region. This or says over here or over here. So it's important to know the difference between how you write your inequalities. So now you should be on to your 901 guided practice.